Today, we're going to pull back the curtain on one single element, an element that's responsible for, well, pretty much everything you see, everything you touch, and even what you are. Yeah, we're talking about carbon, life's ultimate architect. But before we get too deep into the weeds, let's just start with a simple question. What do the medicines in your cabinet, all the plastics that are pretty much everywhere, and the very DNA that makes you, well, you, what do they all have in common? I know, it sounds like a totally random list, right? But trust me, there is a super powerful connection hiding in there. And the answer to that question? It's carbon, of course. The field that studies all this stuff is called organic chemistry, and it's basically the science of the just mind-boggling number of compounds that carbon can form. So, you ready? Let's dive in. I mean, it is really hard to overstate just how much carbon runs the show. Think about it. It's in the chemicals we use in agriculture to feed the planet. It's in the dyes that make our clothes vibrant. It's in the plastics that have, completely defined modern life. And that's just the stuff we make. The actual building blocks of life itself, we're talking DNA, proteins, they are all these magnificent, complex structures built out of carbon. But you know what? We didn't always see it this clearly. For a long, long time, scientists actually believed that the compounds made by living things were special, almost magical. They thought there was some secret ingredient. So let's take a quick trip back in time and see how we completely debunked this idea of a vital force. Okay, so back in the early 1800s, the big idea, pushed by a guy named Berzelius, was that organic compounds had this vital force you could only get from nature. But then, something amazing happened. In 1828, a chemist named Friedrich Wöhler was just messing around in his lab, and he accidentally made urea, a key component of urine, from a totally inorganic material. This was an absolute game changer. Suddenly, the magic was gone. And by 1858, chemists had a real working theory for how atoms bond together. And just like that, a brand new science was born. That one experiment by Wöhler completely shattered the mystery. It proved once and for all that the molecules of life weren't magic. Nope, they just followed predictable chemical rules. And for the very first time, it dawned on us that we could not only understand these molecules, we could actually make them ourselves. So if we really want to get a handle on carbon's genius, we got to learn the basic language of all chemistry. And that language is all about the rules of attraction, or as chemists call them, chemical bonds. This is literally how atoms hook up to form molecules. All right, so there are basically two main ways atoms can link up. First up, you've got the ionic bond. You can think of this as a give and take deal. One atom, say lithium, just gives an electron away, and another one, like fluorine, snags it. This whole exchange creates charged particles, ions, that then get stuck together. But then you've got the covalent bond. This one's all about share and share alike. Here, two atoms, like in a hydrogen molecule, decide to share a pair of electrons between them to form a really stable connection. And this sharing, this is the absolute key to everything in organic chemistry.
Okay, so atoms share electrons using covalent bonds. Got it. But here's the thing. While lots of elements can do this, carbon is just in a league of its own. It has these unique superpowers that let it build an absolutely incredible variety of different structures.
And the secret to all of carbon's power? It really just comes down to one simple magic number: 4. A single carbon atom can always form 4 super stable covalent bonds. Not 3, not 5, always 4. And that one simple rule is the foundation for, well, the entire complexity of life as we know it. So how in the world does it manage to make 4 perfect bonds every single time? Okay, this is where carbon gets really clever. It uses this process called hybridization. Now, you can think of a regular carbon atom's bonding tools, its orbitals, as being kind of mismatched. They're not all the same shape or energy. So what does carbon do? Like a master builder mixing a custom batch of concrete, it blends these raw orbitals together to create 4 brand new, identical, specialized orbitals. And these new tools are absolutely perfect for building strong, stable structures. This whole hybridization thing gives carbon 3 totally different building techniques, and each one creates a unique shape. First, there's sp3 hybridization. This is where it forms 4 single bonds, creating this strong 3D pyramid shape called a tetrahedron. You see this in methane. This is the basic building block for everything from flexible plastic chains to super hard structures like diamond. Then you've got sp2 hybridization.
Here, carbon forms a double bond, which locks the atoms into a flat, rigid plane, a key feature in stuff like graphite. And finally, there's sp hybridization. This is where it forms a super powerful triple bond, snapping the atoms into a perfectly straight line, which you can see in a molecule like ethine. And get this, these shapes are incredibly precise. The bond angles for that pyramid-like sp3 shape are always 109.5 degrees. For the flat sp2 shape, a perfect 120 degrees. And for the straight line S, a dead straight 180 degrees. Look, these aren't just random numbers. They are the fundamental architectural blueprints that dictate the final shape, and because of that, the function of every single organic molecule in the entire universe. Okay, so we've gone from the big picture all the way down to the atomic level. Now let's bring it all back together and connect those simple bonding rules to these seriously complex and beautiful molecules that define our world and, our bodies. Let's take nicotine, for example. I mean, look at it. It seems really complicated, right? But every single one of those bonds and angles is a direct result of those sp2 and sp3 hybridization rules we just talked about. It's that super specific 3D shape that allows it to fit perfectly into receptors in our brain, just like a key sliding into a lock. And that right there is one of the most important ideas in all of chemistry. Shape determines function.
Or how about thiamine? That's vitamin B1, an absolutely essential nutrient we all need to live. Again, it looks intricate, but it's built entirely from carbon's simple toolkit. It's designed to create a very specific shape that does a very specific job inside our bodies.
So when you really step back and look at the entire machinery of life, from the simplest little molecules to the most massive complex proteins, it's not magic, it's just geometry. All of it, the whole shebang, emerges from carbon's fundamental, reliable ability to form 4 stable bonds in these predictable shapes. From the ancient Egyptians using natural dyes, all the way to modern scientists designing brand new medicines in a lab, we have been harnessing the power of carbon for thousands of years. It is, without a doubt, life's ultimate building block. And that leaves us with one final big question. Now that we know the rules of the architect, what are we going to build with it next?